Okay, so thank you for having invited me to that workshop. So it's a very diverse program, I think. So now I was asked to give some overview over our work in electricity market design, electricity market modeling, and that is what I will do. I will just lead you through a couple of papers that we have written on electricity market design from a very particular perspective. Namely, we have a lot of energy-only markets in Europe that are interconnected, so that's kind of zonal pricing design. And what we are doing is we have been developing energy or electricity market models that capture that fact that the players at the market see different signals concerning the network congestion than the regulator would see. Yeah, so to capture the different objectives of the different player in an electricity market. So since I'm an economist, so what drives our research is so the basic challenges of energy market policies, so economic efficiency, security of supply, environmental sustainability, and there are some goals that come along in the last years. For instance, in Germany, where I come from, there's a lot of acceptance issues if you try to set up the electricity system. So there was planned a lot of expansion of transmission lines, and people just don't want it. It's a lot of not in my backyard problems that come with either transmission expansion or even with the installation of renewable supply in front of their doors. So that's some issue that we have to take into account. And in Germany we have a nuclear phase-out. Not everywhere that's the case. I spoke over lunch to a Canadian, and they actually currently build plants. So, and there are also some geopolitical issues that come up that are interesting to look at in energy market models that are mainly due to sector coupling. So a very important issue will be the coupling of different sectors, gas, mobility, heat, and electricity. And one of our goals is to develop our models further in order to capture some likely effects of sector coupling, and to get insights on how we have to shape the market design and taxes and levies in the energy sector as to make the situation attractive for sector coupling approaches. So that's what drives us. So my talk will basically deal with three issues I will focus on and lead you through some research that we've done. One is market design in the sense of designing electricity market, what are the spot market prices that come out, and what are the network fees that are implied by a certain electricity market design. The second issue that is very important nowadays, and I will show you why that is the case in a minute, is taxes and levies. And a third aspect that I will talk about briefly is regulatory uncertainty. And not only regulatory uncertainty in terms of some quantity caps on CO2, but also structural regulatory uncertainty in the sense that we do not know what energy policy does with our electricity market design. Will there be zonal pricing introduced, or even nodal pricing, and all this affects investment incentives quite a lot, and exposes the agents to a significant risk. The prices here, that's electricity prices from Germany, which make clear why all this is an issue. So here, that's the wholesale electricity price, the blue bar. That's more or less equal for all different customers. So private households have to pay value-added tax, but then there are network fees which are significant and which are different for different kind of customers. And then there's also taxes and levies, electricity tax, and also the levy that's due to the Renewable Energy Act in Germany. So that's a significant part of the power price. And you see that varies a lot, and this will of course drive the incentives to which extent use electricity also in other sectors. Okay, so a very important aspect is also whether there are locational prices or not. Also this will drive investment incentives to a large extent, whether I expect to have the same price all over country. That's Germany, that's no surprise. So we are working a lot on the German energy system, so my example that I will put forward is Germany, but in a way the models could be calibrated to also capture problems in other countries as well. So of course here the bars is investment in generation capacity, and you see that if we have would have locational prices, that would have a significant effect on investment incentives and also on the technology mix. You rather get a technology switch then. An aspect I hope I will find some time to cover that, a very interesting aspect is how do electricity prices and taxes and levies affect... now I get rid of my microphone. Let's correct this. Okay, so that's also a graph that will reappear at the end of my talk. That's looking at a projection for 2035 on the mobility cost of different different fuels. So that's conventional diesel fuel. That's the cost of the crude oil, and that's the tax. That's a battery electric vehicle. That's the electricity cost. That's under the current system the tax. And you see that there are significant distortions due to taxes and levies that are very different across different sectors in the energy sector. And these are three different electric fuels that we have looked at: methanol, Fischer-Tropsch diesel, and hydrogen in a carrier. And you see here that's for now an interesting insight. That's electrolysis. That's a part that is due to electricity consumption, and the taxes are low because electrolysis would be exempted from the power tax. So you see that the incentives to engage in sector coupling are very much distorted by our pricing systems and by taxes and levies. Regulatory uncertainty is also an interesting issue, and here one issue is what kind of electricity market design we will have in the future. Another issue might be, will we have a CO2 emission tax? Here you see the European situation right now. There are some countries that only have an emission trading system, some others have both a CO2 tax and emission trading, and some countries have only a CO2 tax. So that's quite heterogeneous. So let's briefly introduce how we approach this problem. And what we have done is, and these are the two seminal papers in this respect, where we developed the basic model that we built on. We have developed a mixed integer multi-level model that captures features of the European electricity market design. That's the main feature is that it captures zonal pricing, which is implemented in Europe but also in other countries around the world. So the market area is divided into price zones. In Europe, this is the case right now. The only countries that have price zones within the country are the Scandinavian countries. And but you could also play around with the model and introduce price zones in other countries. So interzonal network constraints are modeled, and intrazonal network constraints are not seen by the agents on the spot market, but this is dealt with by the TSO afterwards in a redispatch stage. Let's for now, there's a lot of literature that does things that are similar, but I skip it now because just in order to save time, and we can discuss maybe the one or the other paper afterwards. So what our model basically does is to specify a stage where the network investment takes place, and probably other long-term decisions of the regulator. For example, the zonal configuration, if the regulator plans to install price zones, or plan how to expand renewable generation plants. Yeah, this could also be done by the regulator with a long-term quantity goal, for example. This is done. This can be modeled at the first stage. Then the firms, private firms, invest in electricity generation in plants, also at certain locations. So we model also network, so that here at that stage the firms also decide at which node they install their plant. And this is in particular important if we have zonal pricing or locationally different price signals. And then we model number of periods of spot market trading among the firms, and thereafter, after each period of spot market trading, we dispatch, because at the spot markets the agents do not see every limitation through the network, and this has to be dealt with afterwards by the TSO in order to ensure transportability and matching of supply and demand. And if we calibrate it, typically we use here a type year. So all the 8,760 hours of a year that we model here, and we look then at investment and generation capacity expansion from a net present value view. Okay, so this can be translated in a tree-level model, where the first level, the regulator maximizes total social welfare, so the regulator has a welfare objective, and he could, for example, do network design, could expand the network, so that's typically in order to make it to keep it solvable, it's a good idea to let the regulator take discrete decisions here. So then we have a market stage where the firms maximize their profits. So typically, if we want to calibrate it to a larger network, we need to assume competitive firms, but that's also standard in the literature. If you really focus on the interaction of investment and network, then it's very difficult to model strategic firms. You can do this in little models which you can play around, but not in a big one that describes a whole country. They choose generation capacity, and then they produce or demand, and they consider only a restricted information on the network. So only the interzonal links are seen, and the intrazonal links are not considered. And at the third level, the TSO does congestion management via redispatch, and this is a tricky stage here. It's relatively easy to solve the model if we assumed cost-based redispatch, so that the firms cannot anticipate any profits from the redispatch stage. Then we can boil the model down nicely. I mean, it's still difficult to solve, or it's hard to solve for big instances, but we can boil down the model to a two-level model. If we have market-based redispatch or smart markets at this stage, then it's more difficult. Then you cannot boil it down, and then it's becoming a little bit tedious. Okay, so I have quite some information on the mathematics, but I will skip it now. I will sketch just two ways to approach this to solve the model in principle, and then sketch what you can do with it. Just and maybe we can afterwards a little bit discuss on certain technical issues. But I thought, since the audience is a little bit diverse, I wanted to give an overview rather than the details. Okay, so the first approach to solve that is to reduce it to a B-level model. That is relatively easy because the coupling is relatively weak among the stages. In particular, you can join the first level and third level of the model. It's both a welfare objective that drives the decision, and the constraints are the same that the regulator faces. The regulator sees all the network constraints and has the same objective, so you can boil it down and boil it down to a two-level model where at one level the regulator takes choices on network investment and redispatch, and on the other level the market interaction takes place in the sense of investment in capacity and production decisions. So that's basically one approach, and then you can use the KKT, so then the lower level is a concave quadratic problem, and you can show under certain assumptions. Of course, we can discuss a lot about the assumptions. Under certain assumption, you can show that this has a unique solution, which we do in a paper, and then you can use a KKT reformulation and end up at a single level, a mixed integer quadratic program that you can solve, but it takes quite some time. Yeah. So we have a paper where we compare this approach to a different approach where we use a Bender's decomposition. So here we also split the problem into a master and a subproblem, and we do not reduce it to a bi-level problem in the sense of the slide before, but we have a master problem where we have only integer decisions, and a subproblem that we can solve sequentially that consists of the market level and the redispatch stage. And then by introducing additional cuts, you can make it going and solve the problem in a much faster time than with a KKT reformulation. So that's basically the two approaches, and of course you need a lot of assumptions, and the most important ones are that you have competitive firms, and maybe we can discuss particular ones that you're interested in. Okay, so let's show a little bit what you can do with it. So I used Germany as an example for a lot of reasons. One reason is that we have quite nice data because Germany has a network expansion plan. So the German transmission system operators, they develop a plan how to expand the network, and that is quite urgent in Germany because we have all this wind power in the north, and we have decided to phase out the nuclear plants and also to phase out the coal plants, so there's almost nothing left. Yeah, so we are in an interesting situation because in that model, if you calibrate it for the German case, it happens something. There is a network expansion plan, and this network expansion plan gives some idea what the regulator and the network operators think what will be the scenario in 2021, 2030, 2031. And so that's a nice basis of data which you can use and which you and where you can compare your model results to the projection done by the regulator itself. So we use this data basically for calibrating this model. We have a clear plan that is laid out by the TSO, which lines to expand in the future. There are basically 15 transmission lines that are planned that we use as line candidates. We do not, so we have 15 candidates that we evaluate in our model that the TSO builds or does not build endogenously, and we use production and investment costs from some publications. And what we do furthermore is to boil the German network down to 16 nodes, one per Bundesland. So that's of course not quite accurate from an engineering point of view, but it gives us some intuition. So the results give us some intuition what happens on a broader scale if you look at the German electricity markets, and we have quite some connections to the foreign countries, and that's also an interesting problem, how to accurately model these transmission lines at the border, where we also currently have a project ongoing. Okay, so that's what we are modeling, and I will give you some idea what the model does. Then, with respect to price zones, what I will look at is renewables curtailment. That's a big and very emotional debate, at least in Germany, because people think that if the energy is there and it's good energy, you should not throw it away. Yeah? So renewable curtailment is something that the people hate, although it's very rational if the price is very negative to curtail renewables, but this is an ongoing debate. Then what is also a very interesting issue that is debated in Germany a lot is optimal renewable energy locations. So the typical approach is to build them either, there are two objectives, to either build them where they harvest the most, yeah, so wind plant where it's most windy, a solar plant where it's sun shining most. And the second objective that comes up is some negotiation between the German countries, who gets what share. Yeah, so for political reasons, to build them at lower, less productive sites. Yeah, but not and that's not very convincing, but that's happening, and you can also look with the model what you should do. Not only building them at the most productive sites is not always optimal if transmission expansion is very expensive or hard due to acceptance reasons. So then you could look how to implement such things in renewables auction schemes, and I will shed some light on regulatory uncertainty. So let's first look at optimal price zones in the electricity market. So that's some standard research that we have looked at within the last years a lot. We have one paper in energy policy where we show by example that you can really do it badly. So you can implement zones in an energy-only market design that really reduces welfare. Why can you do that? Because the price zones will yield clear investment incentives where to build the plants, but it could be that in the end the plant cannot produce. Yeah, maybe you have to redispatch it all the time. Yeah, so you have to be very careful to do the zoning such that in the end the plants that are built also have the chance to really produce and to transport the energy to the customer. So you can do it very badly. If you do it heuristically, you can end up in zonal configurations that are improving welfare a lot. And what we have recently done is to set up a model where at this first stage of the three-level model you have a graph partitioning problem and you optimally configure the zones. Yeah, that's a nice exercise, and of course for practical application it's limited because you have so many choices. You have the transfer capacities between the zones, which could determine what comes out. You have the configuration of the zones itself, yeah, which node belongs to which zone, and there are many choices, but at least we show that it can be done. And what you can show with this model already is that heuristic that just says you partition the network and use as a heuristic the nodal prices, that is not a very good heuristic. Yeah, so we play around with this model a little bit. Here are two examples. The left one is one with the same number of zones, so you can always fix the number of zones that you want to get out, for example 2 or 3, yeah, and then let the model choose the configuration. This example here has a higher transfer capacity between the zones than the example to the right. And it depends a lot on the transfer capacity between the zones, which countries will be partitioned into which zone. You see that you get fewer switches by zonal configuration, so there's more gas plants and less coal plants that are installed, and this leads to significantly less CO2 emissions. So you decrease by zonal division into price zones here in this configuration. You decrease CO2 emissions because you promote gas and CIP plants and disfavor coal plants. So interesting is also what happens to the price differences, and price differences between the zones. That is, at least if you have a debate in energy policy, that's a very important issue. Very often the price differences between the zones are an issue that impedes political agreement to implement price zones. And what you see is here that in the summer there are no big price differences. In Germany, and this depends a lot on the characteristics of the country that you look at. In Germany, it's the case that you have a lot of wind power in the north and a lot of solar power in the south. And in summer, both are producing heavily, and therefore you don't have so much transmission constraints between the zones. Yeah? Whereas in winter, solar plants do not produce that much, and you have a lot of wind production, and that induces then the huge price differences. What you can also see that if you look at renewables curtailment, there are also two reasons for which you might curtail renewables. And they occur in winter and one in winter more and one in summer more. In the winter here, you have a lot of curtailment if the renewable production does not cover the whole load. Yeah, so you curtail them, although the aggregate renewable production is lower than the load in that hour, and that's due to the transmission constraints, because the renewables are not where the load is. Yeah, and that's the winter months. In the summer months, that does not almost not happen, but renewables are only curtailed in case really the renewable production really exceeds the load. So, and actually these patterns here, I mean, there is a lot of debate whether one could use the renewables that are not that exceed the current load in order to store them or to do something with them. Here you see that this might be difficult. Yeah, that's a very coarse aggregation already, and it's not happening so often. So it means that you would have to build something that is economic already if it runs in very few hours. Yeah, and it's not even clear whether these plants that are curtailed here are all in the same location. So that could be a challenge, which means that you have, in the end, it will be optimal to have some curtailment and some of these possibilities to use the spare power. Okay, so that's basically what you can see out of the model. We have also looked at something that has been debated a few years ago quite a lot, regionally differentiated network fees in order to incentivize investment in generation capacity at the right locations, as a substitute, so to say, for nodal pricing. So just give them money in order to invest in the right locations. And you can easily see using these models that it does not pay off. As it just affects locations. But as long as you don't, as the advantage of the location is not reflected in the price signals, these plants never run. So, and if you compare several of these scenarios, these are these market equilibrium scenarios here, where we place the plants at different better locations than in the current market design, and also at the first best location, it does not affect in any way the number of lines that you have to build, whereas if you have a first best scenario where you also have locationally different price signals at the spot market, it immediately affects the necessary line investment a lot. So, so that's a null result, so to say. What is interesting is, in a way, to look at optimal renewables location. You can model this in the three-stage model. At the first stage, where the regulator takes investment decision, you can let him take investment in line decision, and let the regulator place the renewables. If you do that, you get a energy market, or you get a system, you see what would come out of a system where the regulator adapted his goals concerning a renewable expansion with respect to the location where they should be built, and expects an energy-only market afterwards. And for renewables, the interesting thing is, since they have very low production cost, it's not so important to have the price signals at the spot market right, but it is sufficient to place them correctly. So you can, by doing this decision right, you can realize significant welfare gains already by promoting the right locations, because they always feed in. So it's particularly easy to do it right. And you can then look at it, and these two maps here are just examples. This is the current situation, how it is planned. There's a lot of wind in the north and a lot of solar in the south, and if you would let the regulator choose it optimally, he would place a lot more wind plants in the north, although they are much less productive there, but they're closer to load centers, and you would need fewer lines. And of course, this trade-off depends on how costly line expansion is. We have currently an ongoing project where we look at package auction design that would implement such these locations and also deal with the market power problems that would necessarily occur if you just would auction the capacity of country-wise, because then you have very little competition. You need to induce some competition also across countries in order to make it going. Okay, so that's one insight, and then what is also very interesting issue that is heavily debated is regulatory uncertainty, and there are already some papers on parametric regulatory uncertainties. So if the fuel prices are uncertain, or if the renewables goals are uncertain, this can be included. What we are interested in is how does it affect the electricity market if the agents do not know which kind of zonal configuration the regulator will choose. And in our first approach, we make it very simple. We just have a two-node example, north and south, and run our model in a way that we have investment in network and investment in generation capacity at a stage where there's no knowledge about the zonal configuration, and then the spot market competition and the redispatch takes place after it has been clear whether there's one or two zones. Okay, that's the very simple example. And the interesting insight here is that already, and that's at the first glance of course not surprising. If you really think about the problem, it's not so surprising that already if there's some uncertainty and the cost differences of installation of plants are not so big, if there's some uncertainty whether there's one or two zones, yeah, and some small probability that there's two zones, I rather put my plants in locations that would also work out fine if two zones would be realized. Yeah? If I'm almost indifferent, for example, for gas plants, where the installation cost, the investment costs are not so different at different locations, I would rather place them in anticipation of this uncertainty. I would place them at the right location quite quickly. And here, that's the probability that two price zones are implemented in the end, and you see that, and I have no graph now on the investment. I will explain in a minute what that graph is about. And we look at different ex-ante probabilities that two price zones are implemented, and then look at what happens, who gains, who loses, and so on. And you get, for already very low probabilities of a better market design, you get quite some effects on the investment incentives and also on welfare. And the welfare gains, that's this graph, that is the welfare changes as compared to the situations where you would expect a market with only one price zone. Yeah, that's our baseline. Mm-hmm.
Sorry, just a quick clarification. On the early stages, what are the risk preferences of the trees that are making the
at the moment they are risk neutral. Okay. We are just working on papers where they are risk averse, but in this project they are risk neutral. Here a benchmark is a market with one price zone, yeah, and the bars show what would be the welfare gain if one price zone is implemented. That's the blue bars, and what would be the welfare gain if two price zones are implemented. And you see that if it has not been anticipated, and then two price zones are implemented out of the nowhere, then there's a certain welfare gain. And if it had been anticipated, then independently of whether one or two price zones are implemented in the end, there's a huge welfare gain just because the locations of the plants are so much better. Yeah? And but the additional benefit of implementation of additional price zones, given that players anticipated it already, is low. Yeah? So that's a very moderate model. No, it's only two nodes, but the effect is interesting in a way. But there are a lot of drawbacks, and we are working on some extensions that deal with them. One is risk aversion, but another one is this model has to assume that the regulator does not use this strategically, this uncertainty. Yeah? So you have to assume that this is exogenous, otherwise it does not work. Yeah? If the players would anticipate that the regulator uses that strategically, then this is a very complex setup. But that's the first step, and we just published a working paper on that. And you see also, and in the paper you see some other interesting aspects, also distributional effects, and also who wins, who loses, and you see also that generation technologies with high investment costs are really prone to economic risk in this setup. Now I have some minutes left to tell something beyond electricity markets. So what we are into since 2 or 3 years is sector coupling. One is gas markets, which we have quite some work on. And what I will focus on briefly now is the connection from electricity markets to mobility. And this is interesting against the background that there's a huge debate on the mobility transition, and there's a huge debate on battery electric vehicles, but there's also a lot going on in the sector of hydrogen mobility, and from a modeling point of view, it is interesting how these two technologies will affect the electricity system in the long run. It's very different effects that they have. Battery electric vehicles will induce a demand, and maybe also significant peaks, because they should be loaded at certain points in time, and there's also some approaches to load them in a smart way, but no one wants to wait forever until his vehicle is loaded, and so there are certain things that have to be accounted for, and that will lead to a significant burden on networks if there are many battery electric vehicles. In hydrogen mobility, you depend on the very first stage, the electrolysis, where you produce the hydrogen, and if you project the models into the future, electrolysis plants will be flexible to a certain extent. Yeah, it's not that efficient, but it's not clearly not producing peaks in electricity demand, but it will possibly be a flexibility option in the sense that you can adapt to the current situation, to the current load situation. So the mobility transition in Germany is clearly currently in the direction of battery electric vehicles, if at all, yeah, because so many vehicles are not there yet. So today, here we have conventional petrol stations, but we have also a lot of public charging stations that they are not that efficient as conventional petrol stations. You are there for longer time, so that the number is not that impressive yet. And the hydrogen filling stations are not very many yet, so 55, so you have really to look. You can be happy if you're living close to one. And the same with the number of cars. Of course, this will be changing in the near future. And what we have done in a recent publication is to look at a comparison of different electric fuels. And what we did is to model the whole process chain. Since we came from electricity market modeling, we looked at different electricity market designs in Germany, basically nodal pricing versus energy-only market, and the economic efficiency of different electric fuels under different market designs of the electricity market. And why is that interesting? Now, that is interesting because if you have nodal pricing, then you have regions where you have really low electricity prices for a lot of hours. If you have an energy-only market, that's not the case. And that significantly affects the comparison of different electric fuels, because the electrolysis needs a lot of electricity input. Okay, so what did we do? We considered three technologies, methanol and diesel. That's electric fuels that are well known nowadays. And then there's one technology to make hydrogen transportable. So hydrogen has a big disadvantage that you cannot transport it easily. But if you transport it in hydrogen carriers, then they have the same consistency as diesel and methanol, so it's also fluid. So that's fluids where you can bind the hydrogen molecules to, and you can decouple them again at the filling station. That's basically the system, and that means that has a consequence that will show up here. So that's the mobility cost of driving 100 kilometers we have used our forecasts for 2035 because we have all the data for the electricity market model, and we have worked with engineers in order to assess the cost of the electrolysis plants and the technical configuration that is possible, and have now optimized the whole process chain for different electricity market scenarios. And what happened is this: we have conventional diesel, I already showed you, battery electric vehicle, and then methanol, diesel, and hydrogen in that carrier. And you see that for the different fuels, you have different electricity consumption in their production, and different cost component. So here you need some other inputs. And for the hydrogen in the liquid organic hydrogen carrier, you need a particular filling station, which makes it particularly costly. Yeah, you need to decouple it at the filling station from that carrier, and that means that the filling stations that you would have to build are more costly, whereas the hydrogen is much more efficient than the other electric fuels. Next idea that comes to one's mind, if you see how costly it is to produce them in Germany. So I just noticed that yeah?
The cost of the battery is not in the electric vehicle?
No, that's just driving cost. That's without the cost of the car. That would turn the picture a little bit around, but that's only fuel cost. Of course, you would not. It's not the idea, and I think nobody really believes it, that you drive a passenger car. That it is more economic to drive a passenger car with hydrogen in the long run. It's rather that you will have lorries, trains, and so on be driven by hydrogen technology. But we use a passenger car always in order to have just some comparison, what it means in comparison with each other. If we have for hydrogen a lorry and for a battery electric vehicle a car, or for both a lorry, would be very unfair. Yeah, I mean, it's very unlikely that that a ship, lorries, planes, and so on will not go with batteries. I did not bring here. I just noticed that I did not show the nodal pricing scenarios, and they are much more favorable for the electric fuel stuff. What comes to one's mind if you calculate it for Germany is first, and that's another project we are just running. If you do it on a large scale, this will affect the electricity prices in Germany. So what we did here is to use our model to generate the prices, and then just to calculate the production process of the electric fuel. But if you do it in a large scale, you will affect the prices in Germany or wherever you produce them. So what comes to one's mind, probably there will be other sites worldwide where energy carriers will be produced and be transported to the locations where it's consumed. Yeah, and and there are some sites which are favorable. For example, in Canada, there's a lot of hydropower. Here in Chile, in the Atacama desert, there's a lot of there's very efficient solar power. In Iceland, there's thermal energy. And in Egypt, there's also sites where there's very high, very constant energy provision. If you look at these sites, and then you can again look at the process chain and optimize it, and calculate what does it cost to transport it to Germany or to Europe, and to drive with it. Then you can you first find out which sites are favorable and which are not, which energy sources are rather attractive and which are not so attractive, and you can find out is it comparable with the cost that you would incur producing it in Germany or in Europe, or is it far away in one or the other direction. And what you see is, and here's now our nodal pricing design, what we compare it to now is optimized German energy market with nodal prices, so that it's very attractive to also invest in electrolysis in Germany. So that's the lowest cost that you can get in the current German market. That here is the cost that you get if you produce in Argentina, in Egypt, and in Canada. And you see that the mix, the energy mix, is also quite different. So here you have in Argentina, you have predominantly wind, and in Egypt you have wind and solar, and in Canada you have hydropower, so you use different sources. The energy costs are quite different. You always have this filling station. That's because I use now the liquid organic hydrogen carrier technology here for that comparison. And you can see that, I mean, the takeaway from this is basically that very likely there will be a mix. There will be some hydrogen production in Europe, but there will also be a lot of imports. And it's very likely that the energy trade flows worldwide will change quite a bit if we transform our energy systems to renewable technologies. Okay, so that's basically what I have what I've put together. So main takeaways are that locational investment incentives are important, so for efficiency and also distributional reasons, and ultimately for acceptance of the energy transition, because locational investment incentives would imply that there is some incentive in every region to invest in something or to engage, and acceptance will also be a big issue. Then electricity prices as well as taxes and levies are key for sector coupling, and I think that's a big goal that we should promote to design our system such that these price signals are not distorting sector coupling incentives. And a very important issue is to look also at the new energy trade flows, and not only to look at our energy system in Europe or country-wise, because if you overlook what might be coming from the outside, you may take the wrong conclusions. So we have some challenges for the upcoming years. We will develop our models further. We look at this third stage. We are actually currently working a lot on getting some grasp on this third redispatch stage, so that we can deal with situations where there are locational price signals from that stage, which are difficult to handle in these multi-stage models. Distribution network modeling is also interesting. Gas market modeling, we have a big collaborative research center here where we develop gas market models and engage in model coupling, and we do all this in a research center which is called Energiecampus Nürnberg, which is only to a very small part an energy market design and economic initiative, but we have a lot of engineers on board that do a lot of things here. The chemical and thermal storage guys, these are the ones who cooperate with us in the hydrogen projects. We have a lot of expertise on networks and on solar plant development. Okay, so thank you very much.
There is time for some questions.
In terms of calculating what is the best source in a certain region, what assumptions do you make about the transmission network and the ability to transmit part of the production to a different location?
In the worldwide analysis here,
Or even when you're talking, when you're talking about specific.
here it's shipped, so they are shipped. The hydrogen stored in that energy carrier is shipped to Europe, and then also in our calculations transported by lorry. And it depends a lot on the scale. If the scale is big enough, you would do it by pipe networks.
Right, but let's say that you want to perhaps take advantage of the production of wind power in the northern part of Europe in other areas. Is that something that would make sense to try to use the power grid itself to transmit part of that excess to the south?
It's the only way you can do it.
Right, but what are the limits to that? Is the question? How do you account for those limits within this model?
So to transform it into hydrogen and then to transport it in the south, or what do you?
That's my question.
That's an idea.
The question is also like in the earlier studies that where you were focusing on Europe only. Like what assumptions do you make on the network? Is there like a power grid? Is that the question?
We try to calibrate the network. For example, if we look at it for Germany, we try to calibrate the German network in a simplified version. Yeah, and then we look at the decision whether you should extend the network in order to transport the wind power in the south, or whether you should rather try to induce investments closer to load centers.
All right, thank you.
And for Germany, it's not bing bang. It's something in between. No, you should not expand the network to the such that you have a copper plate. But of course, you should use the efficient sites in the north to a certain extent.
So, like in your 2035 model, you have all these high voltage DC cables.
Yeah.
They are in the
Yeah.
Yeah, but you could take into account the fact that there will be, I guess, a lot of power available in the Nordic countries, and this might change a little bit the trade-off between, let's say, producing down or upwards Germany.
Yeah, we have accounted for it a little bit. We have also in the model, we also model some transit exactly due to that fact that in the Nordic countries there's a lot of power, and it's very likely that in the long run this will be also transmitted into Central Europe, and we capture it in the model already in a stylized way. But that's of course.
Because there is hydro and wind.
That was
I guess to follow up on the both previous questions, probably is a question I can't ask very well in real time, but maybe we talk later. Some studies were done for Western Germany, where if you operate the system better, you don't need to build the transmission grid. In other words, the transfer from northwest to Bavaria is limited by voltage support, not by thermal congestion. And there are presentations on that, so I guess it begs the question about what level of detail you need to represent when you do investments planning versus and how do you link it with different options, which are very low-hanging fruit options on operating the system more efficiently by dispatching voltage, for example, rather than just real power and so forth. You know, sort of engineering aspects of improving the operations, and there's a lot of low-hanging fruit there. In the U.S., FERC is really paying considerable attention to those type of improvements because you really cannot build a transmission grid. So how, I guess the general question is, it's mathematical question, is what type of detail one needs to capture to draw the conclusion that we trust, you know, which is good for the society.
I think it's an interplay between the different the different approaches. I mean, you need the detail on the network and on the network management, of course, but you also need models that tell you, and that's more our expertise. What our models do is they tell you how would the investment decisions taken and where under different regulatory frameworks. And optimization, a network calculation from an engineering point of view could not do that. I mean, they have to assume where the plants are built.
Well, if you optimize the grid and
Yeah, but
connect
that-
operations and investment, that's what engineers do also.
Right, but at the free market, the players do not optimize the whole system, and that's
Right.
and that's the aspect that we are looking at. What at a free market would happen as compared to an optimized system. And of course, our optimized system is not an optimized system that captures all the details from an engineering point of view, but it is a benchmark that we can use in order to compare it to our market model. And that's our contribution to make visible how agents that respond to price signals would take decisions as compared to what should happen if you optimize. So we do not state that we do the network issues completely right. That's not the case, I mean. Okay.
I think this is a good time to thank the speaker again and go for a break.